Hi everyone, my name is Jonah Harris. I'm the Director of Artificial Intelligence and Machine Learning at the Meet Group, and this is High Performance Real-Time Recommendation with Redis. First, a little bit about me. I have a background in database internals, high-performance software engineering, and recommendation system design. I actually started at the Meet Group back when it was a tiny little startup known as My Yearbook back in 2008. And over the years, I moved on from leading the database engineering team to overseeing site-wide architecture and actually becoming CTO from 2015 to 2017. Now I lead the artificial intelligence and machine learning team to build not only recommendation systems, but our moderation and abuse prevention systems. Additionally, I founded my own startup called Nextpress that focuses on database compatibility, and I'm an avid open source contributor, contributing to Redis, as you can see, the syslog support, zrange store commands, some optimizations to geo, and back in the day, we used to do a number of SSE intrinsic optimizations, which never made it into core, but the PRs are out there. The Meet Group is a global leader in personal connection. And what that means is that we help millions of users, millions of people, find connection and community within our portfolio of mobile applications. That's primarily MeetMe, Scout, Lavoo, Tagged, and Growler. We do this by committing to high standards, adopting industry-leading best practices, and really continuous improvement. There's nothing that we look at and say, can't we do this better? Whether that's on the ML side or engineering or even on product. We're always striving to do better. And that's because, we support 18 million or so monthly active users and around 5 million daily active users. In our space, the main problem we're trying to solve, and the one that we looked at Redis for, is personal connection. So within personal connection, there's really a matchmaking algorithm, right? That's performed for professional reasons, whether like LinkedIn, or for dating, gaming, entertainment, etc. And this is usually on a user-to-user basis, recommending one user to another user, or on a user-to-item basis or item-to-user basis, where we're trying to recommend, for example, a video broadcast to a specific user. Now, within matchmaking, there's a significant amount of ongoing research in the academic space on recommendation, right? And from a company standpoint, what we're trying to do is realize how do we take that academic research and develop a system that we can test and deploy at scale. And the key is really at scale. The considerations that we have when we're looking at each of these new academic research papers is, our implementation must be real time. We don't have the luxury of building an offline recommendation model. For the most part, we need to be able to capture that user's attention within, the seconds that we have. And to do that, we really need the most relevant content that we can get at the time. So it must be real time. We must be able to build the system pretty quickly and pretty easily. We don't have months to engineer a system just to test it and see if it's going to work. We need to look at this algorithm and see, is this something we can incorporate and improve a certain aspect of our product? Yes or no, and we need to do that pretty quickly. To do that, we have to support high-performance data storage and access. We have a significant amount of data flowing over our networks. And we need to be able to store it and access it in multiple different ways, not only for recommendations, but for analysis. So we need to do that really quickly. We must be able to scale to support millions of users in a test. Due to social networking effects, a lot of the algorithms to be compared to a control require that the algorithm run in a geographic environment. And we have to run millions of users in that test to be able to see if it's really going to make a difference to our business. And lastly, we have to be able to support in-memory or memory-based recommendations as well as model-based recommendations. So memory being either the full data set or approximations that we can combine in real time in memory, or mathematical models that have already been sort of pre-built that we can incorporate into the results. So when we looked at solutions on the development side, Node.js was a no-brainer to us. It had the best trade-off in terms of performance for engineering effort. And when we looked at developing this, we really split into two components. First, the recommendation requests are handled by a REST-like API in Node. And second, we analyze and process and ingest real-time data for members and interactions between members via a consumer that listens to our RabbitMQ event stream. On the data storage side, we chose Redis. Redis provides fast, persistent, and network accessible versions of all of the fundamental data structures that we need to use. It has support for Lua, which allows us to perform complex logic within the server side close to the data. And then it also supports modules, which allow us to extend Redis for more performance-oriented things that we would need to do in C, for example. So our approach when we look at an academic algorithm and try to improve it is to break down the mathematical components of the algorithm to convert from an offline version to an online variant. What you'll see when you look at most academic research is that very little attention is paid to performing the recommendation or the algorithm online. That's more of a software engineering problem that they tend to look at it as. So we have to take the math that they've put together and figure out how to do that online in real time rather than doing these offline batch jobs. Once we look at that, we determine the data structures that are required, and then we model the data that we have accordingly. Then we determine, based on a combination of locality of reference and tier-based scaling considerations, which logic we need to execute server-side in Node.js, which is more really the application side, and server-side within Redis itself. To do that, we generally try to compare how much data is copied over the network at once to perform the operation, as well as concurrency-related aspects, which is, can we get more out of Redis by pushing everything into a single command rather than having to deal with multiple keys and a lot of back and forth round trips between the server. So once we determine that, we implement a test solution and we test it. The first system that we tried to implement a proof of concept on was a paper called Recon, which is a reciprocal recommender for online dating. And our goal was to determine the time required to implement a scalable and real-time dating-oriented reciprocal recommender based solely off the academic paper from scratch. How long would it take us to implement it, deploy it, and test it to see if it makes a difference? The bounds that we sort of gave to this was one physical server that had 8 Redis server nodes running, each pinned to a specific core. We developed this with a shared nothing architecture so that any core really was on its own. Each Redis instance had every piece of data that it needed to perform the operation locally on that core. And what we did was then shard by member ID so that all of a member's data was on a specific shard or a specific CPU. And when we look at the algorithm in this paper, we looked at breaking it down, and there's really 2 functions to the algorithm. There's performing a compatibility score between one user and another user, and then there's the reciprocal score that is the combined harmonic mean of both one-way scores. So when we look at these, we have specific data structures that are defined in the paper. So we have the user profile, and in the paper there's really only 3 attributes, which are gender, age, and the body type. And then you have the attributes for the user itself, but then the preferences that a user has for those attributes of another user. So when we look at modeling these, we looked at using a couple different data structures in Redis. First is a hash per user, and that hash contains the member attributes themselves. So my age, my gender, my body type. And then what we have is a sorted set of member attributes, and we use this to be able to perform filtering that we'll talk about later. So for every attribute, there is a sorted set, and within that sorted set is members by member ID. And then when we model preferences, which is my interest in another user, that would be my interest in each of those attributes, actually, not just in the user, but in the attributes. And so for that, we have another hash, which is a hash of my interests or my preferences, which is each attribute of members I've been interested in, and a count. The count is really the number of users with that attribute that I've been interested in. And then we have another sorted set, just like we do on the other side, of members with the given interest. And this is actually a running normalized weight of my interest in that attribute. And what we have is an online data update algorithm, so that on profile creation, or if a user updates their profile, we have to be able to set that initial hash of member attributes with the new attributes for that user, and then we have to update the sorted set for those attributes as well. And then on each interaction between me and another user, we need to increment the count of my interest in their attributes, each attribute that's associated with them, and then recalculate the normalized weights and store those in the sorted sets. If we look at the code for that, so adding a member is really done via a Lua function. So we add the member ID and each of their attributes. And what we do is iterate each of those attributes and update our hash of member attributes. And then, as you can see, update the sorted set for each of those as well. And then on the interactions, we again have the member ID that we're interested in and the value of each of those. And so what we do is we first pull in all of the interests for the given member ID, find all of the attributes and increment them by 1, and then we recalculate the normalized scores and add them to that sorted set of interests. And then when we get to the actual recommender, we have a fairly complicated Lua script that we're going to go through, which allows us to perform a set of filtering as well as a top N sort of recommendation. So first, we put in the top N that we're really trying to recommend. Then we have some OR-based disjunctive filtering for any attributes that we're okay with, like multiple values of. So example, I'm interested in people on a search basis between age 35 and 40. So we would be using OR, disjunctive attributes for that. And then we have and or conjunctive filters that we add. So if we want to limit by gender, for example. And then what we do is pass in, because this is a shared nothing architecture, and what we're doing is distributing each query to each shard, is my attributes. So every attribute that's associated with my profile, in this example, my gender, age, and body type. And then what we're also passing in is my interests in the other attributes, and that is the interest and the weight. So as an example, we want to get the top 10 most important people, recommended people, who are age 23, 26, or 30. We want to filter that again conjunctively by female. And then we have all the attributes that are associated with this profile. So tags, what the person's looking for, what their body type is, their gender, education level, etc. And then what we want to also pass last is the interests for this user in the other users that they've demonstrated by actual interaction so far. So what happens is, to generate the list of candidates, We build a sorted set containing all the members who have the attributes in the disjunct or keys. We then build a sorted set containing all the members who meet the hard filter criteria of the conjunctive set. We then build a sorted set of all the members with basically from those users to me, a one-way score using my attributes and their interest in my attributes. And then we take that and build another sorted set, which is me to all the members who have the attributes that I've shown interest in. We then take that resulting one and build a sorted set that contains all possible matches by intersecting both of the one-way sorted sets, the people to me and me to the people. And we take that sorted set, apply the hard filters, the conjunctive filters, and then we perform a final scoring. So we build the sorted set containing the reciprocal compatibility scores, and we do that by retrieving the member's score from the one-way set. We subtract that score from the summation. We then perform the actual reciprocal score, the harmonic mean, and then we take that resulting calculation and put it in a new sorted set. Once we've done that for all the members, we return the top n from that set. If we look at that from a code perspective, I actually have the original piece of code we did for that. And you'll be able to see this in GitHub. So first we have to parse the original request into all the different parts. And this is really just using a simple state machine for that. Then we build a sorted set of all the disjunctions. We build a set of all the conjunctions. We go through for each of the attributes and build a sorted set of them users interested in me. Then we perform step 4, which is the opposite. And then step 5, we build the set of all possible matches by intersecting those. Step 6 is really the more complicated one, where we take all of the possible matches, iterate over them, and then build a reciprocal score of my interest in them and their interest in me. And then finally, in step 7, we just pull the top n out of that. And the results of this were pretty great, actually. We developed this in 3 days. It might have been a little bit of ugly code, but it was our first shot. And we built it in 3 days. All told, it was about 900 lines of code. The response time in Redis was actually very impressive. It was 45 milliseconds at our 99th percentile. And we successfully tested this from a scaling perspective on our single physical server with all users in California. This resulted in a 23% increase in profile views, so me viewing other users. So the reason for that was that they were seeing users they were more likely interested in. And then what we were really looking to do was increase new conversations, and of those profile views, it actually increased new conversations by 15%. So engagement actually was increased fairly significantly. Our key to this was really server-side Lua scripting. So while most users implement the logic for Redis in their application locally, in their application tier, I would say, or in the client, we can't do that. We need to be able to access our Redis-based systems from multiple programming languages, and to do that would require duplicating a lot of code. So what we did was implemented a functional interface, and this was actually very similar to the way we deal with our MySQL and Postgres systems and our Oracle systems, in that the application doesn't really make normal SQL queries to the tables. It actually makes SQL queries to functions, and those functions handle all of the logic, whether it's retrieval or storage or complex queries that are needed. And that allows us to really simplify access to the database. And in this case, it allowed us to simplify access to Redis so that we can access it from C-based code, from our Node.js code, and from Python code. One of the keys to doing this was actually using a preprocessor. We used file pp, which is a generic file preprocessor, and allowed us to take a lot of our Lua code and build a reusable library that we were able to deploy to Redis. And that allowed us to break things out pretty nicely. And you'll be able to see that in the repo on GitHub. Next steps that we took were to build a collaborative filtering reciprocal recommender, an item-to-item recommender, and then we actually built an Amazon personalized clone in Redis that we're working on as well. And one of the nice features of Redis were that because we're trying to split this out onto multiple cores and then distribute to multiple servers, normally to do that you would need a single coordinator, but using PubSub and streams, we're able to actually implement sort of an architecture where each node listens to the other nodes for information that it needs on its own shard. And then the node itself is responsible for doing that, rather than having to have a coordinator and dealing with, sharding out within the coordinator and distribution and all of that. So it's pretty nice. We can deploy a node with a very small piece of Node.js code, and it knows which other systems it needs to listen to and for what type of data. So our key learnings and takeaways really is that used correctly, Redis is far more than a cache or a simple database. We've been using Redis since 2009, very, very early, primarily as a simple database and as a cache when we didn't want to use Memcache. But over the years, we've turned Redis into a very intelligent data store. As you can see, Lua turns Redis into a smart data store. And it's really the Lua scripting that enables us to develop fairly complex algorithms and decide whether we want to run them on the application tier or inside Redis. It gives us a lot of flexibility. And then Redis modules have enabled us to build more complicated or more performance oriented code and integrate it within Redis. So in short, Redis enables us to prototype, deploy, and test new real-time recommendation algorithms at scale. Thank you.